Today we'll talk about solutions of biopolymers, how they form, whether they are stable or not, about specific properties of such solutions, and how to destabilize solutions of biopolymers. So, biopolymers or high molecular weight compounds. This is the abbreviation. You can add W here if you want. Substances which consist of macromolecules, and they have molecular weight of at least 10,000 atomic unit. They are formed from low molecular weight compounds by polymerization or polycondensation. The only difference is that in the reaction of polycondensation, low molecular weight compound is byproduct. The size of macromolecules is hundreds thousands times greater than that of ordinary molecules. And the most important polymers, and they are natural polymers in the organism, are proteins, polysaccharides, and nucleic acid. But we will speak mainly about proteins. Depending on the shape of macromolecules, proteins are divided into two groups. Not only proteins, well, globular and fibrous. That's a trivial classification. You know that proteins have two structures, helical and fibrous. And the helical structure is more typical for globular proteins. Their chains are bent like this. In space, in such a way that macromolecule acquires a shape close to spherical. That's why they are globular. They are soluble in water. And, well, the examples are albumin, for example, egg white, globin, myoglobin, and so on. Fibrous or fibrous protein with fibrous structure usually have pleated sheet structure. And usually they are not soluble in water. For example, like alpha keratin. They have different functions because globular proteins are usually enzymes, hormones, and fibrous proteins have structural and storage function. According to their structure, they can be linear polymers. When here is example. When the monomers form long chains not bounded to each other. Usually they have a high melting point because they can be tightly packed in lattice. And the example is a fraction of starch, amylose, branched chain polymer, like amylopectin. In amylose, we have only 1,4 glycosidic covalent bond, and in amylopectin, besides 1,4, we have 1,6 glycosidic bond. And three-dimensional network polymers or cross-linked polymers form when initial linear polymers are joined together and form such three-dimensional structures. Of course, the most important probably property of um, proteins is their acid-base property. Uh, it's important for DNA and RNA as well, because in DNA and RNA, the centers of basicity are nitrogen atoms in the residues of nucleic bases, and the centers of acidity are the residues of phosphoric acid that link nucleotides. The only one OH group in such residue phosphoric acid is ionized because pH of blood is 7.38 plus minus 0.05. Counterions to such ionized group are usually amines. But in proteins, the molecule of a protein have at least two functional groups, N-terminal NH2 group and C-terminal COOH group. But the side chain can consist of any acidic or basic centers, like carboxylic group in glutamic aspartic acid, like amine group, or a basic heterocycle, like in molecules of lysine or arginine, and so on. And of course, charge of the whole charge of protein will depend on ionization of such functional groups. Isoelectric point, it's not a point, it's a pH value. Isoelectric point is the pH value at which molecule has doesn't have charge at all, or the total charge is zero. It doesn't mean that functional groups inside chains are not ionized. They can be, but the total charge is zero. If we increase the pH value, all acidic centers will react with alkaline added and will turn into anions. That's why at high pH value, much more than pi, a molecule of protein will be in its anionic form. But decreasing the pH value, it means the addition of an acid. All acidic center will turn into their non-ionized form, like COOH or SH or OH, I mean the residue of tyrosine with phenol hydroxy group. But all basic centers, not only NH2, it's just a symbol. It can be a nitrogen atom in heterocycle in histidine. They will be protonated, and if pH is much lower than pi, the molecule of a protein will exist in its cationic form. But these three states are not the only possible state for a molecule of a protein, because let's take, for example, cationic form of a molecule, and let's increase the pH value. Some of these NH3 free group or protonated amines will lose their protons. It means that the positive charge will become a little bit lower, but it still will be positive. That's why proteins can form not only two types of buffer solutions. For amino acids with two functional groups, NH2 and COOH, only two possible buffer systems are possible. The first, at pH lower than Pi, it will exist. It will consist of cationic form and bipolar. And if pH is more than Pi, it will consist of anionic form and bipolar form or zwitterionic form. In the first buffer system, bipolar form will be conjugate base. In the second, when pH is more than Pi, zwitterionic form will be conjugate acid. But for proteins, as two forms, as the difference between two forms can be only one, for example, positive charge. It means that a molecule of protein can form a set of different buffer solutions. In at isoelectric point, a molecule of a protein has a very specific property. First of all, it doesn't have a charge at all. And but a molecule still has positive and negative charges. Just the amount of them, the number of them, is the same. They will interact with each other, and the molecule will twist, forming the so-called globule. It means that in isoelectric state, the proton molecule in the solution will occupy the smallest volume. If we increase or decrease the pH value, the molecule will straighten out and the diameter will increase because groups with the same charge will repulse. The absence of and this tight, the absence of charge and this tightly packed structure means that protein in this globular form won't interact with water molecules. First of all, no charge, and water molecules are polar molecules. And tightly packed structure, water molecules won't be able to penetrate inside this globule. And the film of bounded water in globular form of a molecule of protein will be very thin. What does it mean for stability of a protein solution? No charge, very thin absorptive layer of water. It means the stability of solutions of protein at pH equals Pi will be the lowest. Of course, the addition of any charge, positive or negative, will increase the absorption of water, and molecules with the same charge will repulse. So the stability of protein solutions will increase while pH increasing or decreasing with respect to isoelectric point. The property of um, the ability of a molecule to have positive or negative charge at different pH values is used in electrophoresis. This is the migration and separation of charged ions under the influence of an electric field. An electrophoretic system consists of two electrodes with opposite charges, anode and cathode, and between them uh, there is a gel filled with buffer solution. Of course, when we molecules with different charges will move uh, to cathode or anode. It depends on their charge, and with different rates. The higher will be the charge, the higher will be the rate of such movement. This property allows, first of all, to separate protein molecules depending on their charge. For example, we can add into this system a buffer in which all proteins except only one will be at its isoelectric point. It means that their electrophoretic mobility will be zero, and only one proton will migrate to the corresponding electrode. That will allow to isolate such protein from the mixture. Of course, the electrophoretic mobility will depend on particle size, particle shape and charge and temperature, but using different values of these parameters, it's possible to separate them. Electrophoretic analysis is widely used in forensics to compare, for example, DNA in medical laboratories, to do genetic testing in microbiology, in chemical labs to purify samples of protein. And moreover, by comparing, if you have a sample of a protein with well-known structure, this method can be used for identification of proteins. This is the real electrophoretic plate. This is my daughter's hand. So the plate is real, colored with a special dye, and these spots in this electrophoretic plate corresponds to individual protein. That's how it looks like. uh, solutions of biopolymers. They have some properties similar to properties of true solution, but at the same time, properties similar to colloidal solutions. They are listed here. Um, And the properties that resemble true solutions are the following. First of all, they are quite stable, like solutions of lower molecular compounds. Then they are convertible. It means that if you dry, for example, remove all solvent from a solution of a protein and get uh, a precipitate, and after that you will add the solvent again, you will turn your polymer into solution again. And one more property um, is that dilute, but very dilute solution of high molecular compounds can be homogeneous systems. But the forces of attraction between molecules of polymers is rather high. So usually if you increase the concentration, they will form colloidal systems. So for very dilute solution, we can say that they are homogeneous systems, but usually they are not. Uh, even if it is a homogeneous system, the size of dispersed phase, size of particles of high molecular weight compound are same as in colloidal solution, up to 10 to minus 7 meters. That's why the diffusion of such molecules, they have great size and high molecular weight, and of course it will slow down the diffusion in such solution. And due to their extremely great size, molecules of high molecular weight compound cannot pass through semi-permeable membrane. Uh, this property this property is used in dialysis. In dialysis, uh, this technique, dialysis technique, is used to separate molecules based on their size. Uh, if you have a mixture of molecules of high molecular weight compounds, they are blue here, and the particles of low molecular weight compounds, well, for example, ions or salts or something like that. And you put it into a bag uh, made of semi-permeable material. Usually it is microcellulose or cellulose acetate, something like that. After a while, the equilibrium, and put this bag into a solvent. After a while, the equilibrium will set up because the particles of lower molecular weight compound uh, can pass through this semi-permeable membrane, but molecules of high molecular weight compound cannot. So as a result, you will purify if you remove now the solvent with particles of low molecular weight compound, mm, almost pure uh, sample of high molecular weight compound will be in this bag. In medicine, dialysis is widely used uh, for people whose kidney can no longer perform these functions. And it is used to remove excess water, solutes, low molecular weight particles and toxins from blood. So it is called hemodialysis. Hemodialysis, and this is the scheme of artificial kidney. The blood is removed from the body and then pass through dialysis machine through this artificial kidney. Uh, Low molecular weight compounds, excess of water, all toxins, they will go into um, dialysis fluid and it will be removed and replaced with fresh portions of dialysis fluid, and blood will return to the body with the help of dialysis machine. Besides features that resembles true solutions and that are similar to colloidal solutions, high molecular weight compounds have a very interesting property that low molecular weight compounds do not. And this is one more additional stage in the process of dissolution. It is called swelling. Uh, Swelling is the increase of volume and, of course, the mass of high molecular weight compound due to adsorption of a solvent. It consists, this step, this stage, swelling itself, consists of two stages. Uh, at the first step, only a small amount of a solvent will be absorbed. And these, let's speak about protein and water, will be easier to explain. Molecules of water will penetrate, will be absorbed on molecules of protein, forming bounded films of bounded water. Due to, well, dipole-dipole interaction or ionic dipole interaction or just van der Waals forces. But as new bonds will be formed between a molecule of a protein and molecules of water, the process will be exothermic. Delta H as the first step of swelling is negative, and of course we will get more ordered structure. It means that delta S or entropy change will be negative. But as you remember the process, I hope you remember delta G is delta H minus T delta S. The process is spontaneous while delta G is negative. The second part of the equation, T delta minus T delta S, will be positive, but the first delta H is negative. The absolute value of this part of equation will be more than the second. So at the first step of swelling, delta G is negative. At the second step of swelling, these hydrated molecules of a protein will go into the bulk of a solvent, into water, forming, well, true colloidal solution, usually colloidal. And the heat effect of the second step is approximately zero. But of course, due to even distribution of these hydrated molecules throughout the bulk of the solution, the entropy of the system will increase. So at the second step, delta G also will be negative. So the process of swelling is a spontaneous process. It is characterized by a swelling degree alpha, uh, which is the ratio of M or V here, mass of polymer or volume of polymer after swelling, M0 and V0 before swelling. And if you calculate swelling degree using masses, then of course M minus M0 will be the mass of a solvent absorbed. Of The swelling degree depends on many factors, and first of all, the nature of polymer and the solvent, because there is a good rule in chemistry: like dissolves like. So polymers with polar functional groups, uh, like proteins, for example, um, the degree of swelling of proteins in water will be high. But if you put the sample of protein into benzene, of course the degree of swelling will be lower. But the resin will swell in benzene, but not in water. What else? Oh, I forgot. So if polymer-polymer interaction are strong enough, you won't see the second stage of swelling. You just get a gel. I'll speak about them a little bit later. Uh, Molecules of polymer in gel form a network solid structure, and inside here in these cells there are molecules of solvent. But if a polymer solvent interaction is stronger than polymer polymer interaction, then these weighted molecules of protein will go into solution, and limited swelling will turn into unlimited swelling. You will get a solution. So everything depends on nature of polymer and solvent, interaction between molecules of polymer, and temperature, of course, because at low temperature, swelling can be limited, but if we increase the temperature, the kinetic energy will increase, and limited swelling can turn into unlimited swelling. You can get a solution of a polymer. Of course, the degree of swelling depends on pH value, and you will have such questions in your online test. So how the degree of swelling will depend on pH. Here we have to go back to the term isoelectric point. I show this slide again. The shape of a molecule of a protein in its isoelectric state, tightly packed, and the total charge is zero. Of course, the amount of water that can be absorbed by a globule will be much lower than the amount of water that can be absorbed at pH more, which is more or less than isoelectric point. So this is the plot of graph how the degree of swelling depend on pH value. Uh, it will reach its minimal value, the degree of swelling, at pi. And this is one of the methods that can that allows to determine the isoelectric point of protein, because it's difficult to calculate it if for individual amino acid molecule we calculate pi as half of sum of 2 pKa. Then for protein it with a lot of functional groups in side chains, uh, how you will calculate this isoelectric point. This is one of the methods. Then the presence of salts. Uh, the degree of swelling, it depends on the nature of salts, because salts can be hydrolyzable or not. If it is a non-hydrolyzable salt, so it does not undergo the reaction of hydrolysis, it means that the presence of such salt doesn't change the pH value. Then everything will depend on the ability of ions of this salt to absorb water. The Hofmeister series, in Hofmeister series, cations and anions are in order of their ability to absorb water. For example, among cations, the ability of ammonium cation to absorb water to form its own films of bonded water is very high. Among anions, probably one of the best is sulfate anion. So if we compare the degree of swelling of a polymer in water or in sodium sulfate, not ammonium, but sodium sulfate. Sodium sulfate is non-hydrolyzed salt. The presence of ammonium sulfate doesn't change the pH value of a solution. In a solution of sodium sulfate, the degree of swelling will be lower than in pure water, because sulfate anions will absorb some free water, and the amount of water that, well, should penetrate into molecule of protein will be lower. But a salt can be hydrolyzable. For example, ammonium sulfate. The medium in solution of ammonium sulfate is acidic. And again, if we compare, for example, the degree of swelling of a polymer with isoelectric point lower than 7, we will compare it in test water or in solution of ammonium sulfate. In ammonium sulfate, it will be lower, but not just because of the presence of these cations and anions, but one more factor will be important. The decrease in pH value in such solution. So two factors will be added. Uh, the second property of polymers solution that uh, that is absolutely different from that of property of lower molecular weight compound is uh, the difference in their viscosity. Viscosity is just a friction between molecules of moving fluid. Uh, but molecules of lower molecular compounds have small sizes, small diameters, and molecules of high molecular weight compounds, their diameter is great. That's why the viscosity, even if you have solutions of high molecular weight compound and low molecular weight compound with the same concentration, the viscosity of solution with high molecular weight compounds will be much higher. Uh, of course, the viscosity will depend on pH because the shape of the molecule depends on pH value. At isoelectric point, um, molecules of polymer will form globules, and the diameter of globules will be smaller than at the other pH values. And of course, the viscosity at pH equals Pi will be the lowest. So the plot, how the viscosity, you just have to change alpha by any other letter that will mean the viscosity. But the plot will be the same. And this is one more method for determination the Pi value of proteins. Pressure will affect the viscosity of high molecular weight compound. You cannot observe such property for solutions of lower molecular weight compound because for such solutions, viscosity doesn't depend on pressure. But for high molecular weight compound, yes, it depends. And when you increase a little bit the pressure, external, the molecules of polymers will be oriented along the stream, and it will decrease a little bit the friction between layers of this moving fluid. So the pressure will decrease at first time. So two specific properties that high molecular weight compounds have, but low molecular compounds um, do not. Uh, One more stage in the process of dissolution, and this is swelling, and this, well, mm, strange dependence of viscosity of pH and pressure. Temperature, of course, will um, decrease the viscosity. Now, the stability of solutions of biopolymers. They're quite stable, and this property resembles the solution of lower molecular weight compounds, uh, but but if uh, we are talking about proteins, if factors of stability of solution uh, will be altered, uh, property a solution of protein can give a precipitate. First of all, pH, I said about it. At Pi equals pH, the stability of protein solutions is the lowest because molecules uh, can interact with each other. They do not have charge and they do not have these protective films of bounded water. But if the native secondary, tertiary, and quaternary, if any, but because not all proteins have quaternary structures, if uh, these structures will be disrupted, then the native form of a protein will turn into its denaturated form. And denaturation, the process of denaturation, uh, will lead to formation of precipitate. Factors that can cause denaturation. Well, as all factors that will break the bonds due to which the secondary, tertiary, and quaternary structures exist. First of all, this is hydrogen bonds, because secondary structure uh, forms due to the formation of hydrogen bonds, intermolecular hydrogen bonds. Well, first of all, it is heat and ultraviolet radiation, because the absorption of excess of energy will increase the kinetic energy, and parts of molecules will move freely, and it leads to um, disruption of these hydrogen bonds. Then the change in pH value, because if we increase or decrease the pH value, we change the charge of functional groups in the side chains of proteins, and it will lead to uh, the absence of the charge, of course, will disrupt these hydrogen bonds. Uh, it can be caused by addition of salts of heavy metals and organic solvents. And again, if, for example, side chain of a protein includes SH functional groups, the residue of cysteine. You know that mercury and lead cations uh, forms uh, form precipitates with the sulfide anions. It's insoluble compound. So such cations can interact with form. Well, it's not won't be salt. Well, we can say that this is a salt. Will be like bridges between um, two SH groups S, then mercury, for example, and again S. And in such case, SH group won't be able to participate in hydrogen bond formation, so it will lead to denaturation. Organic solvents, due to the presence in not all of them, of course, but those who have carbonyl group, for example, like acetone, because carbonyl group of acetone can participate in hydrogen bond formation instead of carbonyl group of the original um, protein. Urea has the same carbonyl group and moreover an H2 group. Uh, Copper sulfate, the high concentration of copper sulfate can cause the denaturation because copper likes to form copper ion, cation, likes to form halide structures with amino groups, and free amino groups of proteins can form these complex compounds, and they won't participate then in a hydrogen bond formation. So all these factors will cause the denaturation. The process of sorting out, this is the second, um, well, way, method how to destabilize a solution of a protein. The result will be the same. In both cases, in process of denaturation and process of sorting out, you will see precipitate, but the mechanism is absolutely different. Oh, I forgot to say whether denaturation, the process of denaturation is reversible or not. It depends on what structure is broken due to the process of during the process of denaturation. I've never seen a boiled egg um, turned into a native state. So if it is a quaternary or probably tertiary structure, maybe the process can be reversible. But I doubt that if it is secondary structure, doubt that denaturation can be reversible. Uh, let's go back to sorting out. So in both cases, you will see a precipitate in denaturation and process of sorting out. But mechanism is absolutely different. For denaturation, if it proceeds due to the alteration of hydrogen and other covalent bonds inside the molecule of high molecule of protein or between molecules of protein, if it is uh, quaternary structure. Then salting out is the formation of a precipitate after addition of some amount of salt. That's why it is called salting out. A very small amount of a salt can even stabilize the solution of a protein. It is called salting in. Uh, Ions of salt penetrate inside the molecule of protein, interacting with different charge group, and it increases a little bit the diameter of a molecule of protein, allowing water to be absorbed inside the molecule of protein, increasing these protective films of bounded water and stabilize as a result the total system. But at high concentration of a salt, the process of salting out will take place. And the reason is, again, the ability of cations and anions of a salt added uh, to absorb water, because uh, any cation and any anion in aqueous solution, all of them are hydrated, all of them are covered with absorbed water, uh, thin films of bonded water. Now, just imagine you have a solution uh, of a protein. It consists of molecules of protein and molecules of water. Now we add salt, it dissociates in water, and cations and anions of this salt begin mm, to absorb water. It means that the amount of free water in which uh, our protein was dissolved, the amount of this free water decreases, but the less the amount of water, we just decrease the amount of solvent in which our polymer was dissolved. Of course, it will lead to formation of precipitate. Uh, the process of salting out is reversible. It's a reversible process because as soon as you remove the agent that led to formation of precipitate, the salt, uh, polymer will be dissolved in solvent again. So if you filtered this precipitate after that, washed our ions of salt that caused dissolving the formation of precipitate, and after that put this polymer, your enzyme or protein into water, you will get a solution again. One more type, very interesting type of uh, structures that high molecular weight compounds can form uh, is gels. Uh, this is, it cannot be called a solution, but it's not a solid. In gel, the dispersion medium is structured molecules bind with van der Waals forces or covalent bonds, molecules of high molecular weight compounds. And inside the cells, between these molecules, or even inside these molecules, there are molecules of liquid water, for example. Such systems have very interesting property, and the first one is called thixotropy. Gel itself is a non-flowing structured system. uh, because the number of covalent bonds between molecules of high molecular weight compounds is very high, and then they form this structured system, three-dimensional system. Uh, but they can be diluted by stirring. Uh, and then they can go back to gel in a resting state. This is the phenomena of thixotropy. So this is the example with ketchup. You know, it doesn't flow if you turn over the bottle, but if you shake it or stir it or, well, do something, it will flow. But after a while, molecules of solid phase will form this structure again, and this gel will turn into its initial state again. These thixotropic transformations can be repeated many times. Mm, uh, it is a reversible process, uh, and thixotropy is one of the proof that the structure formation in gels occurs mainly due to van der Waals forces. In a human body, the example of thixotropic system is synovial fluid. Synovial fluid. And the second, to my mind, interesting property of gels is synergesis. This is a decrease of volume of a gel due to the removal of part of the water. Well, over time, like here, this is initial state, and this is the state of the system after synergesis. This is solvent, liquid, enriched with molecules of polymer. Um, Over time, the number of bonds between polymer chains in gels increases, and the initial structure of gel is compressed, and a part of a solvent with molecules, small amount of molecules of polymer will be released from initial gel. Such process, um, synergesis, occur when the bread jelly dry up, and this is an example, well-known example from our everyday life. Uh, this is yogurt only, and this is yogurt after synergesis. This is the liquid phase enriched with high molecular weight compounds. Only 1 day in the fridge uh, was enough for synergesis to take place. Synergesis occurs in the aging process of the body. It is established that with age, uh, mm, the gradual change in spatial structure, tertiary structure, and decrease in the hydration of protein molecules occur. And as a result, the tissues become more rigid and less elastic. And that's why, for example, uh, the veal steak and steak uh, made of old cow have absolutely different taste. And this is one more example. Uh, Vitros can undergo syneresis, and this process is important for ophthalmology. Well, that's all I wanted to tell about solutions of biopolymers. Thank you. The lecture is over.